Hi, this is Jaydeep Sai, and the topic which I have selected for this TikTok video is signal processing for time of flight imaging sensors. Let's discuss the introduction. A brief history of computational imaging. A picture is worth 1,000 words. Throughput Throughout the past several centuries, this immemorial phrase has pushed development of photography from analog to digital, accelerated by breakthrough advancements in sensor technology. The digital revolution created a necessary for sophisticated signal processing algorithms tailored for image enhancement, storage, and compression. Shannon's sampling theory was the pathway for analog to digital image conversion. The classical Wiener filter was used for image enhancement. So, we are discussing the brief history of the computational imaging, and it's about a picture is worth 1,000 words. So, a picture can depict 1,000 words. Just a photograph can worth 1,000 words without saying anything. So, throughout the past several centuries, this immemorable phrase has pushed development of photography from analog to digital. So before the imaging was done using analog, and now at the current age, it's done by using digital techniques accelerated by breakthrough advancements in sensor technology. So we are using the sensor technology and advancement is done in the sensor technology. So for that, digital image processing. The digital revolution created necessary for sophisticated signal processing algorithms. So this digital revolution made the enhancement of the sophisticated signal processing algorithms. So many signal processing algorithms were developed for the digital revolution for image enhancement. So for the image enhancement, signal processing algorithms were made, and also for the storage of the image and for the comparison of the image, many sophisticated signal processing algorithms were developed in the history. Shannon's sampling theory was the pathway for analog to digital image conversion. So in the history, we can see that the image used to be in the analog phase, and by using the Shannon sampling theory, we can make the analog image to the digital image. The classical Wiener filter was used for image enhancement. Transform domain coding utilizing discrete cosine and wavelet transforms played a pivotal role in JPEG compression over the last few decades. With the advent of wavelet transform and compressed sensing theory, the field of signal processing has undergone a philosophical reformation. A field that was once heavily reliant on smoothness assumptions now uses principles inspired by the notion of sparsity. Until the last decades or so, the fields of image sensor technology and signal processing ran in parallel to one another, with minimal interaction or exchange of know-how. So, in the transform domain coding utilizing discrete cosine and wavelet transforms played a pivotal role in JPG compression. So, in the JPG conversion of the image, the discrete cosine and wavelet transforms played a crucial role, and it also played a pivotal role, which means the crucial role. Over the last few decades, with the advent of the wavelet transform and compression sensing theory, so many theories were made in the image processing world. So that were compressed sensing theory, and also many transformations like wavelet transformation were done in the field of signal processing, has undergone philosophical reformation. So many reformations were done, and many modifications were also done in the signal processing, a field that was once heavily reliant on smoothness assumptions. Practitioners of this computational imaging photography ideology have devised many solutions which were previously not possible when individually adding functionalities to the sensor architecture or use a more sophisticated processing algorithm. For example, consider the problem of motion deblurring that arises in conventional imaging. Wherever an object moves under during sensor exposure, it causes pixels to smear across the frame, resulting in a blurred image. In the context of signal processing, this is an ill-posed problem that has been well exposed within the theme of deconvolution. So, practitioners of this computational imaging, so many developers of this computing, imaging, and photography ideology have devised many solutions which were previously not possible when individually adding functionalities to sensor architecture or use a more sophisticated processing algorithms. So many developers made many algorithms which added the functionalities to the sensor architecture for the imaging. For example, consider the problem of motion deblurring that arises in convention imaging. So in the convention of the imaging, the blurring action is performed for that whenever an object moves during sensor exposure, it causes pixels to smear across the frame, resulting in a blurred image. In the context of signal processing, this is an ill-posed problem. So in the context of signal processing, the blurring was a problem, ill-posed problem. But in the imaging, it is a well explored with the theme of deconvolution. The key problem that the exposure time defines a temporal filter, which is essentially a box filter that annihilates any high-pass spatial information. Consequently, algorithmic sophistications alone is not enough. Blurring may be avoided by a shorter exposure time, but this comes at the expense of low signal to noise ratio. It is clear that neither deconvolution nor the sensor level adaptation in itself suffice for a solution to be the deblurring problem. The distinct role of computational imaging emerges when one considers the so-called flutter shutter approach. So the key problem is the exposure time defines a temporal filter. So exposure time defines a temporal filter, which is essentially a box filter. And it is clear that neither deconvolution nor the sensor level adaptation it itself suffice for a solution of the deblurring problem. The distant role of computational imaging emerges when one considers the so-called flutter shutter approach. Time of flight revolution is another topic. So the time of flight revolution principle explores the idea that distance and time are proportional quantities. So this time of flight revolution is a principle which suggests that the distance and time are proportional quantities. As the name suggests, time of flight is the round trip time between the source and a destination taken by a particle or a wave. Hence, knowing one entity is equivalent to knowing the other. So by knowing the particle, we can depict the wave, and if we detect the wave, then we can detect the particle according to the time of the flight principle. Nature is replete with examples that rely on the TOF principle, which is time of flight principle. Bats, dolphins, and visually impaired human beings use the TOF principle for navigational purposes. 3D imaging with TOF, time of flight sensors. So how the 3D imaging is done with the help of time of flight sensors? Let's discuss. TOF sensors are active illumination devices consisting of an illumination unit capable of probing a scene with an amplitude modulated light that is not necessarily coherent. We call this amplitude modulated waveform the probing function or P of S, Y, T wave. X, y are the spatial coordinates and t is the continuous time variable. For simplicity of exposition, we will consider per pixel processing and simply with p of t. The probing function interacts with the scene response function, which is called as SRF in short. Interaction results in the reflected signal R of t. The reflected signal is observed at the TOF time of flight sensor. This is characterized by its transfer function that we refer to as the instrument response function, which is called as IRF in short. The IRF models the sensor's electro-optical assembly. For example, the IRF for digital camera is the point spread function of the lens. The interaction between the reflected signal and the time of flight sensor results in the measured signal M of t, which is converted to digital signal via sampling. Precise mathematical description of the time of flight imaging pipeline is discussed in box 2, TOF image formation model. Based on the TOF image formation parameters, which are P, H, and O, one may now define the specific inverse problem at hand. This is also true of other wave-based time of flight modularities. Radar, sonar, ultrasound, terahertz, and others. A distinct feature of the consumer TOF sensors is their use of lock-in principle, which implements the cross-correlation operation. So the precise mathematical description of the TOF imaging pipeline is discussed in box 2, that is TOF image formation model. Based on the TOF image formation model parameters, which are E, H, do, one may now define the specific inverse problem at hand. This is also true of other wave-based TOF modularities, which are radar, sonar, ultrasound, terahertz, and others. A distinct feature of consumer TOF sensors is their use of the lock-in principle, which implements the cross-correlation operation. Optical multipath interference and spectral estimation, which is multipath interference, or which is called as MPI in short, is a problem that naturally occurs in communications, escorts, and array signal processing. Consumer grade TOF sensors are designed to work under the premise that each point is the scene maps to a single pixel on the sensor. Whenever this hypothesis does not hold, the TOF sensor measures are erroneous due to MPI. So the multi-path interference, which is called MPI, is a problem that naturally occurs in communications, Scottish and array signal processing. Consumer grade TOF sensors are designed to work under the premise that each part in the scene maps to a single pixel on the sensor. Wherever this hypothesis does not hold, the TOF sensor measurements are erroneous due to MPI. Landscape of inverse problems in TOF imaging. So let's discuss the landscape of inverse problems in TOF imaging. Having covered the mathematical basics of time and frequency domain, TOF imaging systems, we will now discuss case studies where signal processing theory may be used in combination with TOF sensors to solve inverse problems. So we have seen the time and frequency domain of the time of flight image system. Now let's discuss case studies where signal processing theory may be used in combination with TOF sensors to solve inverse problems. Optical multipath interference and spectral estimation. Multipath interference or MPI is a problem that naturally occurs in communications, escorts and array signal processing. Consumer-grade FDTOF sensors are designed to work under the premise that each point in the scene maps to a single pixel on the sensor. Whenever this hypothesis does not hold, the TOF sensor measurements are erroneous due to MPI. This results in corrupted 3D images. For example, this can happen when imaging through a semi-transparent object such as glass window. So in the optical multipath interference and spectral emission is a problem that naturally occurs in communication. This results in corrupted 3D images. We can also give the example such as when imaging through a semi-transparent object such as glass window, this phenomenon can occur. Fluorescence, lifetime imaging, and system identification. Fluorescence lifetime imaging, which is called as FLI in short, is a problem of interest across several disciplines of science and engineering, with the notable example of fluorescence. Lifetime macroscopy, this imaging modality finds applications in a number of fundamental problems, including DNA sequencing, tumor detection, fluorescence tomography, and high-resolution microscopy. Like the TOF sensors, FLI can be categorized into time domain and frequency domain modes. Time domain FLI. TD-FLI utilizes an impulsive light excitation pulse, which is used to probe a fluorescent sample. Wave sensors motivate a demand for forward models and algorithms that can handle this new wave of data. A handful of algorithms inspired by signal processing community have been used to tackle inverse problems in optical TOF, but significant and numerous challenges still remain. So many challenges still remain. Current efforts are directed at establishing empirical results with a rare discussion on design of efficient algorithms, fundamental limits, or performance bounds. So the TOF sensors motivate a demand for forward models and algorithms that can handle this new wave of data. While optical TOF sensors are a recent phenomenon, other TOF systems such as ultrasound, seismic, and radar technology have been around for decades. The knowledge transfer between optical and other TOF systems is far from reality. Each TOF modality have its own idiosyncratic constraints which stem from the physics of the problem. However, there are commonalities that are shared by all of these systems. By discussing specific case studies, we take a first step towards the goal of bridging this gap. Conclusions. Now we have come to the conclusions of the topic. So the conclusions and future directions. So the conclusions are TOF imaging pipeline. So imaging pipeline is done in the image enhancement of the image processing by using the time of flight, which is called TOF, and the probing function. The probing function is used in the image enhancement and algorithms and fundamental limits. So there are many algorithms and fundamental limits which were proposed by the practitioners of the signal processing, which are used by the help of the convolution, which makes the images blur, and which was the problem in the signal processing, but later it has become the necessary for the image processing. By using the deconvolution processes, the image was enhanced, and another one was modeling non-ideal reflections. I thank the faculty and college for providing this opportunity to speak on the topic. Thank you.